High-fidelity interactive rendering of virtual environments is a computationally expensive process, and parallel computing is usually employed to alleviate this cost. Traditionally, such parallel systems are composed of expensive dedicated resources which are not readily accessible to all users. A typical office or a university lab has idle resources which can be harnessed for compute power without additional costs. We present a method for high-fidelity rendering at interactive rates on inexpensive variable resources such as a desktop grid. This effectively enables the majority of users that work in small to medium companies or universities to experience interactive high-fidelity rendering on their desktop machines when other users' resources are left idling. Our fault-tolerant algorithm is capable of handling runtime variation of resources, as shown in this video. The counter on the top left presents the frame rate and the number of resources. Our method is useful for an architect or an archaeologist when visualizing a building under different lighting conditions. It provides a preview tool for a product designer to test different object materials. An animator can use it to have a quick look at characters in a fully rendered environment before submitting the final frames to a render farm. A user would not be able to try out all of these different settings in an offline rendering environment, as it is a time-consuming process. Our method would allow this at low cost by connecting all the available machines into a desktop grid. To the best of our knowledge, our method is the first to handle interactive rates on a desktop grid for high-fidelity rendering. Traditionally, an image is subdivided into tiles for rendering in parallel, and then composited together to obtain the final image. However, when rendering in a volatile environment, all these tiles are not guaranteed to complete successfully. In such a case, the failed task would usually be rescheduled. While rendering at interactive rates, the time margins are small, and the rescheduling of missing tiles would inhibit performance. In our method, we subdivide the image space into pseudo-randomly chosen sets of pixels, such that each task offers a fair coverage of the image. If some tasks fail, the partial frames thus obtained can be reconstructed to estimate the final image. Unlike traditional methods, this allows the users to interactively render using volatile resources. Our method follows a master-worker paradigm, and we schedule the workers on the available resources of a desktop grid. The master sends out a job to the worker which processes it, and then sends the results back to the master for composition. During the computation, a worker may become unavailable, and the job assigned to it would not be completed. We use reconstruction to deal with such faults instead of traditional fault tolerance mechanisms such as redundancy. First, the user interacts with the scene, defining the rendering parameters for a frame. This frame is then divided into sets of pseudo-randomly chosen pixels, which are queued up as jobs. When an idle worker connects, a job from the queue is sent to it to render. Once the results are received, the partial frame is sent to the GPU for reconstruction and display, and the whole process is performed continuously at interactive rates. The frame reconstruction starts with the partial frame being reconstructed using the nearest neighbour algorithm, while considering spatial discontinuities. It then checks if any user interaction has taken place since the last frame. If there's been no user interaction, results are accumulated and displayed. If the user has interacted with the scene, a spatio-temporal filter is applied taking into account discontinuities. This cuts down the temporal noise before the frame is displayed. Our method renders dynamic scenes at interactive rates, where the user can change an object's colour, position, or material. All this can happen with change of resources at the runtime. In this clip, we show the luminance values of the pixels computed by a path tracer on the workers, which is then reconstructed by the master. This fast-forwarded section shows how a static image converges progressively while accumulating results from the workers. The red pixels have a high probability, while the green pixels have a low probability of being perceived differently using a visual difference predictor metric. The grey pixels represent no perceivable difference compared to the gold standard image. We show 4 videos of the kitty scene being rendered at a fixed frame rate on different number of resources. The figures on the screen show the amount of resources used for rendering the corresponding video. The resources for the bottom right video vary as a sinusoidal function. With a lower number of resources, the method relies more on reconstruction, deteriorating the visual quality while maintaining a fixed frame rate. This section shows the VDP comparisons for 3 videos using the video rendered with 96 resources as the gold standard. With a higher number of resources, the images converge much faster while rendering at a fixed frame rate. We have presented a novel fault-tolerant interactive rendering algorithm. This algorithm enables users to achieve high-fidelity interactive rendering at a low cost using volatile computing resources such as a desktop grid.